Hello, my name is Chris Passaglia and I'm a professor of biomedical engineering in the medical engineering department of the University of South Florida. My research is focused on the areas of ocular neuroscience and neural engineering. And what we're interested in is trying to understand how we and other animals see, and to use that knowledge to engineer novel technologies to address diseases of the eye. So we've been developing technologies for a long time. One of the first technologies that we developed was a microelectrode for recording from animals that are moving around freely in the ocean. The microelectrode consists of a shell that seals the inner conductive media from the extracellular fluids. In this case, it was an animal that crawled around in the ocean. And it recorded the signals being transmitted from the eye to the brain by individual optic nerve fibers. So more recently, here at USF, my lab has gotten interested in developing technologies that are focused on a disease of the eye called glaucoma. This disease is associated with a high intraocular pressure, or high eye pressure, that develops slowly over time as an individual ages. So one of the technologies we've developed in my lab to continuously monitor intraocular pressure in a live eye is this device here, which can record eye pressure every second or a few seconds, or faster than that if you so desire. And thereby we get a lot more data than one would traditionally get if you went to an eye clinic and you got an eye puff or a tonometer touch on the cornea of your eye. You get measurements every month or two. As a result, we learned a variety of things about the intraocular pressure signal, such as that it's not static, but continuously varies from second to second, minute to minute, and from day to day. And then we can use a device such as this one here to continuously not just measure intraocular pressure, but this device can also inject fluid into the eye to raise and lower pressure to whatever level we desire. And it can measure how much flow needs to be injected to do that. And so we can both measure pressure as well as the flow that needs to be injected into the eye to produce a pressure change, and thereby measure the resistance of the eye to fluid outflow. Why the brain exerts this circadian modulation of intraocular pressure is a subject of future investigation. What is unique about this lab is we not only engineer technologies to record the signals generated by neurons, or to measure intraocular pressure continuously in a live eye, but we also test those devices out in animal models to make sure that they're functional. We don't just sort of send those devices off for somebody else to test. And thus we get feedback as to device performance, which we can then use to modify the device design. In addition, we also use these technologies to then address scientific questions about how the eye is functioning. So reach out and explore the impact you can have with the USF Medical Engineering team. Go Bulls!